excited to present data from a new project that I've been working on in my lab, where we're looking at changes in both the flowering and the realized niche for our study species across 150 years. Now, I'm going to give my talk with three sort of chapters. The first chapter, I'm going to introduce my study system. Then I'm going to talk about some broad phenological changes that we've seen in the species and the climate factors that drive them. And then finally, I'm going to introduce you to some stuff we've been doing to look at how the flowering niche has been changing or not changing through time. So first of all, this is Tritannus perfoliata and the companion Acaceae. I happen to think that it's an awesome study system for all kinds of stuff. I think it's particularly tractable for studies of phenology and niche evolution. One reason for that is that it's extremely common. So camping in the Ozarks with my family, I came across an awesome population, so I had to improvise, because I had to get some. So I collected it and put it in an Nalgene bottle. Somewhere in here, someone has some because they have it for me. So when you find it, it's very common. So there's a lot of locality data on it. And in addition, as you can see here within the continental US, it's extremely widespread. Now, for the duration of this talk, this will be the geographic extent of my analyses, and that's simply because that's where we have phenological data available. But it's worth noting that perfoliata does extend into Central America and parts of South America as well. Okay, so extremely common, widespread, tons of data. Next thing that makes it really handy for phenological studies is that it has a breeding system that allows us to identify the peak flowering window. So in studies of phenology, peak flower is commonly used, and so this is nice because it makes our data comparable to some of these other types of studies. Okay, so how do we do this? In perfoliata and all species of Tritannus, individuals make two types of flowers. So it's dimorphic cleistogamy. So the first type of flower is what you're seeing here, sort of on unexciting cleistogamous flower. There's absolutely no corolla. It's obligately selfing, so nothing's ever exposed to pollinators. And these individuals tend to make cleistogamous flowers first. So there's a temporal pattern here that we're going to take advantage of. After this, all individuals will make hasmogamous or open flowers. So all you really need to know is that it's your sort of open, or what I think is pretty cute purple flowers that the species makes. So because individuals make cleistogamous flowers, then open flowers, followed subsequently by a few more cleistogamous flowers, that means, if we see a voucher specimen that looks like this, with lots of purple flowers on it, we can with some confidence infer that we're looking at the peak flowering window, so we can take advantage of that. Okay. The other thing that makes this species really ideal for these types of studies is that it has a really extensive digital herbarium record. So I think people vouch it a lot because they come across it all the time, and it's pretty cute. And as you probably know, more and more herbariums are starting to digitize their collections. So this means that if I have an internet collection and some really tedious hardworking students who will do tedious things, we can database all these phenological records. All right, so we did this. There were thousands and thousands of records. When we vet the data and sort of compile it down to what has a completed data set, so things that have locality and phenology data, you're looking at the spatial distribution of that data with the black square. So we have about 1,200 data points ranging from 1863 to 2016. So this is a pretty nice data set for a phenological study. And the other thing you might be thinking when you look at this is that it's a long time period. But what's the temporal depth? Is it biased sort of to one part of the sampling range or not? And actually, the temporal sampling depth is pretty evenly distributed throughout that sampling range. And so in some places we have quite a bit of data going back over a century, which is pretty neat. But overall, you can see that where we did sample, shown in the dark black blobs, we have a pretty good even sampling depth across here. Okay, so we got tons and tons of data on phenology. What did we find? Okay, so there's the first part of data I'm going to show you. So we found that overall, across this range, Tritannus perfoliata is advancing in its flowering time. So this is similar to what a lot of people are seeing in a lot of species. So these are box plots of peak flowering date by decade. And in this model, this was our geospatial analysis, latitude, elevation, and year were all significant predictors of variation in flowering time. Okay, so it's flowering earlier. That's neat, especially when you're looking across such a large geographic logical question is, okay, it's advancing, so what are the climate factors that might be associated with this shift? And to address this question, we took advantage of the PRISM climate group, that's hard to say, data set. Specifically, we used monthly averages for 6 different climate variables. So that means for every single one of those points from 1895 on, we were able to download the appropriate climate information for that time point in that GPS locality. Now, in the interest of sort of time and clarity, I'll just say that we dealt with autocorrelation among those climate variables by generating principal components. And so this multiple regression had principal components for climate variables along with year. And so this first part isn't too shocking. So we again found in that model that flowering time is advancing and that climate and year explain a significant proportion of that variation. But the more interesting question is which of those 6 climate variables is most important? So which of those relatively does the best job of explaining that variation? And to figure that out, we used a mathematical method developed by our collaborator, Jason Brown, in 2014, where you can figure out the relative contribution of factors in a principal component loadings. So here's the gist, here's the Cliff Notes version of all that. When you look at all that climate data, the most important factors, or the best predictors of that variation in flowering time, are things associated with temperature. So Tmax, Tmin, temperature, dew point. This is probably what most of you were expecting. Temperature is important for flowering annuals. Okay. Neat. Okay. So, like a lot of people, we wanted to see how spring climate might be behaving at our sampling localities. And since this is a spring flowering annual, what I'm showing you here is climate data from March, April, and May. That's what that stands for. And I'm just going to show you one example so I can make my point. So at those localities through time, you can look at climate, for example, daily maximum temperature, and who'd have thought it, in general, spring is getting warmer earlier. So this is probably what you all expected. Okay, so one thing we noticed when we were examining our data is that the range of values in which you saw flowering occurring was relatively narrow. And so we decided to explore that. So if you map on here, those same climate parameters, so in this case, this is maximum temperature, during the month of flowering, this is shown in gray, the variation in those data is much less, and that trend line tends to be more shallow. So what does this mean? Well, it occurred to us that what we had done is we had collected climate data that allowed us to start to understand the flowering niche, so the range of parameters in which you might expect flowering to occur. The other thing we suspected by looking at this is that that flowering niche was relatively stable through time. However, as some of you seem to have noticed, based on your expressions or hopefully interest, is that this isn't a niche, right? So if we want to look at that niche space, we have all the data that we can do that, so we did. All right, so this is looking at the flowering niche through time. I'm going to show a few graphs like this, so if you just bear with me. On this axis, you're going to have all the decades here, so these are averaged over a decade, and because I'm showing the niche in 2 dimension, I'm just showing you the major principal component here. Okay, so this is a niche that is developed or modeled using all of those climate parameters. So this is kind of what we expected. This flowering niche overall seems to be pretty stable through time. Okay, so we're starting to see something going on here. I'll convince you with stats in a minute, I promise. But there's a lot more that goes in a plant's life cycle beyond flowering. It has a whole other part of its life history. And because Portfoliata is so common, it was really easy to get locality data. So we were able to build a realized niche over about 4,000 data points. Okay, so here's where I think it gets really cool, is that you can see that the realized niche is changing in pattern through time. Again, I'll throw some stats up in a minute. So these dotted lines or dashed lines here are just reference points to make it a little bit easier to look through here the different decades. And I will tell you that the median value here for the realized niche does shift through time. Okay, so we believe we're seeing a pattern where the flowering niche is quite stable, the realized niche seems to be changing in behavior. This looks really cool, but we all like stats. So I wanted to be able to test this statistically. And you can do this with something called an equivalency test. So this is a test that can be used to test for a niche similarity between 2 different species. So we're going to use it here, and instead I'm going to test for divergence or similarity among decades in either the flowering niche or the realized niche. Essentially, this is a resampling method. So you take all of your observed data and you pull it together, reshuffle, resample it randomly into the two groups, and you do this for many iterations to get your null distribution. Okay, then you can see if that niche similarity falls within or outside that null distribution. So what does this look like? Okay. First, I'm going to show you what we found for the flowering niche. These are essentially pairwise comparisons. So this heat map gives me the ability to show a lot of p-values all at once without hopefully making anybody's eyes cross. And again, here are those decades as I promised. So these are just decadal comparisons here. There's a method to my madness. I'm going to fill this in. Okay, so values and squares that are purple, that are more dark, are close to 1. And so you don't see a difference in niche space between those decades. When the square is more yellow, then you're approaching significance. In a couple cases, we do have differences in the flowering niche between decades. Okay, here's where it's cool. If I could do a drum roll, I would do it. Can anyone do that for me? Thank you. All right, so here's what you get when you look at the realized niche. So when you compare the realized niche from one decade to another, we see a lot of divergence. So that pattern we thought we were seeing, where the flowering niche appears to be quite stable and the realized niche is changing through time, we have really compelling evidence that that is actually occurring. So I think this is really cool as we get more and more research into phenological responsiveness to climate change. Really cool research, I saw some this morning, is looking at what the consequences of these shifts could be for the species as a whole. So here we have an interesting case study in which the flowering niche is stable through time, yet the realized niche has been changing. So if you didn't follow the niche part, you should understand that the flowering niche by design will always be in the realized niche, of course. But we don't know if they change dramatically over time, how that would affect flowering or fitness or other life history traits. Okay, so we're out of time. So hopefully now you love Tritannus perfoliata. You're going to see it everywhere. I showed you that, like a lot of other spring flowering annuals, we are seeing advanced flowering, and that is associated with climate. And then maybe I introduce you to this new concept of how we can look at niche space through time to better understand consequences for species that are undergoing these shifts, which invokes the next question, which is how do we go from here? I think the most charismatic question is to look at the fitness consequences of this, but I don't have great greenhouse facilities or anything where I can do that. However, I do like data. Since I'm short for time, I'll just plug this. Tritannus is a relatively small genus, and so I actually have phenological data for all 7 species in the genus, and we do have evidence that 4 of them, one of those is perfoliata, are shifting in their flowering through time. I also have the climate data for all of these species, so it's just a matter of analyzing it, but we're super curious as to whether we're going to see similar patterns in these other species. So we really need to know whether this phenomenon is occurring at a broader evolutionary scale, and other people should do it in their species. All right, so finally, I don't have a lot of funding, but I do want to thank our universities for sending us here and supporting us. And these 2 amazing women researchers who did the databasing that, frankly, a lot of undergraduate researchers were not willing to sit down and do. They are awesome. Here's Naomi presenting some of the database. And with that, I think I have some time. I'll take a couple of questions.